All right, we're going to start in. Thank you again for rushing through the lunch line. We're very excited about shifting to the second portion of our program, which is about SWIFT, the Sustainable Water Initiative for Tomorrow. Just rolls off the tongue. And please do try the purified water over there on the table. I'm going to introduce our two speakers. I think you're going to go back and forth together, right? So Ted Henifin joined the Hampton Roads Sanitation District on November 1st, 2006 as general manager. He previously served for 9 years as Director of Public Works for the City of Hampton. I know he knows many of you all through that. He holds a Bachelor's of Science in Civil Engineering from the University of Virginia, and he's a registered professional engineer and president of the Virginia Association of Municipal Wastewater Agencies. He's a member of the Board of Directors for the National Association of Clean Water Agencies, and he serves on the Management Committee for the U.S. Water Alliance's Value of Water Coalition. And what he doesn't put in his bio is he's a man of vision. Charles Bott is the Director of Water Technology and Research at the Hampton Roads Sanitation District, where he manages technology innovation for HRSD's 13 wastewater treatment plants and collection system. Charles is a professional engineer, a Class 1 licensed wastewater works operator, and a board-certified environmental engineer. And you all are in for an extremely interesting presentation, and there will be time for questions afterwards. Thank you.
Thank you, Elizabeth. So I was reminded it's always great as a lunchtime topic to have your wastewater folks get up in front of you and talk about wastewater. So it's a little different twist maybe than our normal lunchtime conversation. And as Elizabeth said, there is some of our purified water over there that was 48 hours ago was in a little different form. And it's very tasty today. So with that, we will get on with what we're doing here for you today. Really appreciate the opportunity to be here. I thought I had to be on stage with someone from the Eastern Shore based on the rest of the day has all been fairly Eastern Shore, and Charles does hail from the Eastern Shore, so we'll share this presentation a little bit. So I always open up with a little quick reminder that we've been at this a fairly short period of time because John Smith was referenced earlier by Louis. He was the first person here to start polluting the bay, and we've been trying to clean it up only for a short period of time on that timeline. So we were formed in 1940. And we were actually formed out of, we're talking all morning about oysters and aquaculture. The reason we were formed was in the beds that were condemned in the Hampton Roads in 1925. People were getting sick from eating the oysters there. Of course, at Old Dominion, we don't move too quickly. It took about 15 years to come up with a proposed solution, and we actually went to public referendum in 1938, where it failed. We couldn't get along as a region then either, and it was a nasty political battle, and the folks against forming a regional entity to deal with clean water were not able to get a majority, and they retooled it and came back in 1940, and we actually were formed by public referendum. So we like to think of us as the first grassroots water-focused environmental organization in Hampton Roads. So who are we? We're a little different. For those who don't know, we are a political subdivision of the state. The governor does appoint our commission. We have 8 commissioners. They're typically citizen leaders. It's not a lot of cachet when you help your buddy get elected governor and you get appointed to a sewer board. Cocktail party conversation just isn't as good. So we get folks that really just want to give back in service to the Commonwealth, and we've got a great commission, very supportive of clean water and doing the right things for the Commonwealth. Just quickly, we serve about 1.6 million people, or roughly 20% of the folks in the Commonwealth. We have a large service area. It goes from the Middle Peninsula all the way down to the Carolina line. And so we process about 150 million gallons a day. We've got capacity to about 250. It's a real challenging business proposition when you really sit down and think about it. If you were in manufacturing, you had no control really over the volume or quantity of your supplies that came in, and you had highly regulated and exacting specifications for your product at the other end. I don't think many of you would go into that business. It's a very challenging business from that perspective, and that's really what we're after. This is the area we serve. We've got many treatment plants, 14 actually, but really 9 large ones, and the ones we're going to talk about today, there's 7 of our 9 large ones that we're really focused on. So we really, the largest plant we have is an ocean discharge in Virginia Beach near Dam Neck, and then the rest of them are spread out, either discharging to the James River, the York River, and we do have 1 small plant that discharges into the Rappahannock. So really we've identified these as the 5 main water issue challenges for the region. I don't think any of us would argue that restoration of the Chesapeake Bay is number 1. And we do use the term sea level rise, but we did throw in the appropriate politically correct Virginia term of recurrent flooding. And then depletion of groundwater resources, which is an interesting twist for us, and including the protection from saltwater contamination. And then we'll talk a little bit about wet weather sewer overflows, which nobody likes coming out of the pipe, but it does happen from time to time. So this is really current state of wastewater in Hampton Roads. So we basically treat our water to very exacting standards and discharge it really at the end of 3 major rivers. It goes right into the bay and out into the ocean with no downstream uses, no beneficial use from that point forward. In our region, about 80% of the water we treat comes from surface water sources, and about 20% is from the ground. So the regulatory uncertainty is really the driver behind this from our original concept. So we were sitting around talking about what's it look like in 50 or 100 years. You heard some of the Planning District Commission folks talking about the need for forward-looking planning, and that's what we were doing when we started really thinking about wastewater treatment as you move forward, because frankly, it is a pretty archaic system. We just, as a country, actually as a world, we just send it downhill to the lowest spot, and we've added on some treatment over the years, but we've pretty much been doing it the same way since the Romans figured out you just push it away from your developed communities. But as we looked forward and tried to understand where we would be, the one thing that came into clear focus for us was that regulations will continue to change on our business on a fairly frequent basis. The pace at which things are found, discovered, it outpaces the ability for us to remove them from the wastewater. So the technologies really to detect is advancing faster than the technology to remove. And so we recognized that we really wanted to look for ways that we might be able to find some regulatory stability going forward. And this is an example of some of that uncertainty. So for the TMDL, total maximum daily load, Chesapeake Bay cleanup, we're part of 3 different river basins, like I said, James, York, and Rappahannock. On the James River, 7 of our plants discharge in the James, and we've got an allocation, a waste load allocation for nitrogen and phosphorus for those 7 plants in total. And just to give you some idea, prior to 2000, roughly, we were discharging about 8 million pounds a year of total nitrogen into that James River watershed from our various plants. That's in total. In 2005, when Virginia started to address waste load allocations and passed the laws in 2006 and the regulations requiring us to reduce that discharge, our target was set, our waste load allocation was 6 million pounds. And we had 5 years to reach that. So that was 2006. That was established as a regulation and a waste load allocation for HRSD. Before we could reach that 6 million pounds, if you're following the timeline, 2010 is when the TMDL came into play. So the top line is the 6 million pound line that we were targeting for, and each of those blocks represents at least a $50 million investment in infrastructure. 2 of them represent in excess of $100 million in infrastructure. But by the time the TMDL came out, so we hadn't even got to the first compliance year under the Virginia waste load allocation when it went from 6 million pounds to the red line of 3.4 million pounds in 2022. And the delta between the 6 million pounds and the 3.4 is about $500 million worth of investment that we're making to get there. EPA, in fact, I think Jeff Corbin may have actually made this statement a couple times with his Mr. Whiskers picture. The federal backstops under the TMDL really point to the point sources, to the wastewater treatment plants. And so while 3.4 is our current goal, if it looks like we aren't going to make the TMDL from Virginia's perspective with agriculture and stormwater, we would face a backstop somewhere about 1.6 million pounds for this particular watershed, the yellow line. And the difference in cost between the red line and the yellow line is probably about $750 million additional investment we would have to make to get to that point. So just keep that in mind. That's the kind of changing regulatory environment that we really have little control over, but we're trying to plan around. So our thought process was, let's take our water all the way to drinking water, and maybe the regulators won't do anything more to us. Not saying we're going to get there, but we're not challenging anyone to think of something else we can do with it. But the idea of adding advanced treatment to the end of our existing treatment plants, which are very highly treated water now, and make it all the way to drinking water, we get a very valuable resource. And the idea was, what could we do with that valuable resource? And about that same time, DEQ started really, after years and years of trying to sound the alarm about the groundwater issues in eastern Virginia, really started getting folks' attention with some proposed permit cuts. So these things came together in our minds, at least, that if we're going to make drinking water and there's a groundwater shortage in a drinking water aquifer, perhaps those two need to go together. So our thought was add advanced treatment, go to drinking water quality, pump it into the aquifer, and then we had these other benefits that we hadn't even started out thinking about, which was first, of course, reducing our discharges to the Chesapeake Bay. So that earlier graph that showed the 1.6 backstops, we actually get way below that, and I'll show that to you in a minute. We reduce our discharges by 90%, total discharge into the Chesapeake Bay. We reduce the rate at which land subsides. If we get a lot of USGS works going on around this, but it looks like we can slow down the land subsidence. There's a portion of it related to aquifer compaction. I'll talk about that for a minute. The sustainable source of groundwater. Again, we're putting potentially 120 million gallons of groundwater in a day, and we've modeled that, and I'll show you what that looks like. And then creating some protection from saltwater contamination going forward. So the first piece of this is treating wastewater to drinking water. And again, you're free to taste it over there. It's not exactly new science. It's been done throughout the world, and even in Virginia, Upper Occoquan's been doing indirect potable reuse for a number of years. We're testing two processes, and Charles is going to talk a little bit about the technology when we get towards the end of this. Putting the water into the ground, again, nothing new there. It's being done in many places in the country, and including city of Chesapeake uses the aquifer as a storage area. They use an aquifer storage and recovery unit, and they've been doing that for many years and have put about 2.8 billion gallons of water into the aquifer successfully and pulled it back out. A lesson here, and we'll talk a little bit more about that, is that you need to match the groundwater chemistry if you're going to be successful there, and we'll talk about how we plan to do that. So really hitting these few water issue challenges one at a time. The restoration of the bay, same chart I showed earlier. The white line's been added to the bottom. That would represent the discharge. So we won't eliminate our discharges entirely. There'll be wet weather periods when we will have to discharge, but we will have reduced our nutrient loads significantly. So in this case, in the James River, total nitrogen will be down around 500,000 pounds a year as opposed to our 3.4 million pound allocation. And so that gives us some opportunities, and especially for the Hampton Roads area, we're really focused on how we might be able to offset some stormwater needs through some trading. So the far left column is our current bay allocations for each of the river basins under nitrogen, phosphorus, and sediment. Our post-SWIFT loads in 2030, when we plan to be done, is the next column over. And that leaves a large balance available for other needs, so trading with other folks that need to discharge into the Chesapeake Bay. And our stormwater regional needs are indicated in the far column, and we can meet all of those with the exception of the sediment in the York through this project, and we meet them significantly with plenty of excess capacity to spare. So what that says is we potentially can trade with our MS4 localities in Hampton Roads and eliminate their need to do retrofits. And there's still a lot of work to be done on the stormwater side going forward to make sure that we don't continue to increase load. And there's also the recurrent flooding issues that our stormwater utilities need to be dealing with. But this is sort of not having to go back and deal with the sins of the past. We can trade that off and get them out of the retrofit business. And according to the estimates, that can be anywhere from $1 billion to $2 billion savings for the region. So again, we've already allocated or already discussed the fact that by doing this, we potentially save a $750 million unknown if we had to go down to backstop levels. And here's another $1 billion to $2 billion savings for the region as a result of this project. So the groundwater resource piece, these are some photos out of a USGS publication. Probably a little hard to see from the back, but essentially this is a confined aquifer. The top of the Potomac aquifer is about 300 to 500 feet below us. It's got a thick impermeable clay layer on top of it. It's pressurized because the water enters along the fall line. Where back at the turn of the century, if you penetrated that clay cap, water would rise naturally out of the aquifer to about 31 feet above sea level. So the picture on the left is actually just that, water free-flowing out of a pipe that has gone into the Potomac aquifer. And that was great at the time, so you didn't need a pump, you just needed a valve on the pipe that you had going into the aquifer. The picture on the left, or the right, a little harder to see, but a farmer has a watering trough there. And in 1927, it was at the top of that where the water free-flowed out of the ground. And you can see every couple of years he started, the first time he adjusted, he went to the trouble of putting a T, and then as he realized the water pressure was going to continue to fall, he just started drilling holes because he realized that this is a bit of a problem. And in just about 10 years, he lost about 2 feet of head right there. So a real good indication that as we started using the water out of the Potomac Aquifer, we were already starting to draw the head pressure down early in its lifetime. And since that time, over the last 100 years, we've brought down about 200 feet since then. This is a quick summary of the permits as they're out there in current use. So what we asked modelers to do was project current permitted use forward 50 years and see what that looked like. And that's the heat map on the left. The reds, browns, and yellows are all negative pressures. The crater shows up in the middle, and we won't go into great detail about the crater, but essentially water doesn't move in or out of the crater footprint. And then taking the exact same model, and at our treatment plants, which are the green dots, show up a little bit there at the bottom, sort of around the edge of the crater, putting our water into the aquifer over that same 50-year period at about 100 million gallons a day. And it ends up creating positive pressures in a great deal of the aquifer on the southern side. You still have a little bit of negative pressures are right around the two largest withdrawers, and some negatives up above West Point there, but significantly less negative than they were prior to us putting water in. This was really the map that really got us excited about the project, because frankly, we didn't think putting water in at our treatment plants would make this big of a difference. So there's actually a positive effect all the way north into Maryland and well down into North Carolina. We create a pressure ridge that really helps keep salt water from intruding at least along the southern side of the crater. So the travel time of the water is related to that, and it's a little hard to understand because what I just showed was pressure. So this is pressure, not actually water moving through the pressurized aquifer. When we put our water in, the modeling is, they really can't show us a map. The model is done in 1 mile square cells, and over a 50-year simulation, our water doesn't move out of that 1 mile. So from our injection well, it moves very, very slowly. They did some estimates, anywhere from 3 feet to 30 feet per year, roughly, is how fast that water is estimated to move. It obviously won't all move at the exact same speed, but essentially moves very, very slowly away from our wells. So this is, we're talking pressure, not actually water moving through the aquifer. Adaptation to sea level rise. So again, USGS has estimated that about 50% of our subsidence issue in Hampton Roads is due to aquifer compaction. So, 50% of sea level rise in our region is due to the land settling, and 50% is due to the ground rising, so the net's that 100%. About 50% of that land subsidence issue is estimated to be due to aquifer compaction over time from over withdrawal. USGS did these contours several years ago. The greatest rate at which our aquifer is compacting is in the areas where we're pulling the most water out. So it definitely has a correlation, it seems to make sense. And this is some evidence of that impact. So there's 2 extensometers that were put in by USGS back in the 80s to measure basically the difference in thickness between bedrock and the surface of the land. So, obviously, if you talk to geologists, bedrock moves too, but this is just an instrument that measures the distance between the bedrock and the land surface. Essentially, it's a rod that goes down to bedrock and then is attached to a beam at the surface level. These 2 instruments, there's one in the Franklin area, one in Suffolk, were basically abandoned due to lack of funding in 1998. I see David's head nodding, which seems pretty crazy, but it is a federal program, and you know what happened. So they lost funding. They no longer were monitoring them, but they did continue to go out every now and then and check on them. It was simple machinery. It wasn't anything electronic at the time. And so the picture taken in 2002 on the left with the yellow line shows that's essentially leveled out at that point. They went back in 2015 and took a picture of the same instrument, and you see the sharp angle. When I first saw the picture, we're all talking subsidence. I thought, wow, we're really sinking. And then you really process that, what they're looking at there, and that's land rising 32 millimeters over that period of time. And so, of course, that begs the question, if we're talking about subsidence, why are we showing a picture of land rising? The Franklin paper mill shut in 2010, was shut down for about 3 years, came back on at a significantly lower withdrawal. So really, most of this, we can theorize, again, we don't have data from all the years it was shut down, theorize that most of this occurred during the 3-year shutdown. So we had some recovery of land of 32 millimeters roughly in that area in about 3 years. Really holds out some hope that if we put water back in the aquifer, we may at least slow down, stabilize, or even recover. So we've actually done some modeling. And the modeling shows that from 1890, which they went back to, I guess, their 0 point from land use modeling where we would have been flat, to the 2064, which sounds like an unusual date, but we ran a 50-year simulation from 2014 to 2064. So the chart on the left is aquifer compaction over that period of time due to withdrawal. And the dark browns down in the Hampton Roads area and around Franklin are about 2 feet total compaction over that period of time. The telling tale is we put our water back in, and over this next 50-year period, part of that simulation, we essentially eliminate all of that aquifer compaction. We get it back to the 1890 levels. In fact, there's a short, the darker blues and grays or greens right in there are about a 1/4 of a foot potential increase in the top of the aquifer over the 1890 range. And again, that's aquifer compaction, modeled simulation, best information we have at this point. We won't guarantee those results. Sort of like your broker, you know. So what whether compliance issues, and this ties in just from a funding and scheduling standpoint, but just the top chart shows what shows up at our treatment plants, the blue line. What comes through your water meters, our customers' water meters, is the green line, and the difference is really what gets into our system from inflow and infiltration, so rainwater that gets into our system. It is a separate system for those of you from other parts of the state. It is not a combined sewer system. This is separate, but I'd argue that there is no such thing as a separate system. They all take some rainwater in at some point. So we lose in a bad year less than about 0.015% of the 151 million gallons a day we move. And just some idea of what that looks like from a design flow, volume discharge. So obviously don't discharge at our design flow. It's the far left side bar. Current flow is around that total volume. With our wet weather plan, we'll be essentially discharging the same amount. The SSOs avoided by modeling, again, are about 5 million gallons a year, 270 million gallons over 50 years. Our swift discharge is that little tiny bar, again, because we're putting most of the water into the ground, and the reduction is the big bar at the end. So significant difference to the environment, to the water environment as a result of this project. This is, again, showing nutrient loads, TN and TP, pre and post swift. So on the sewer overflow issue, we really think that a better approach, and we're under a federal consent decree to eliminate sewer overflows, and that's estimated to be $2.2 billion. We owe a plan to EPA in 2017 that's going to help us reduce that, and that's where we get the reduction of about 270 million gallons of overflows. But we're finding some better ways to deal with our bacteria-impaired waters locally, is going out and looking for the actual cause of the bacteria impairment. We've got a small group that's now working with localities to do that. We've had some success on the Lafayette River. We've had some success in Hilton Beach. We're not going to claim victory there yet, but we've been focused and working with Newport News in that area. And we think we can do a lot more on the bacteria impairments other than just spend the $2 billion on overflows. So, SWIFT, this project, the idea of putting the water in the ground, doing this under a phased approach. A lot of folks think it's moving too slowly. I know at the State Water Commission there was some comments about why can't this go any faster. It's not being held up by any regulation or any other issue. We're just moving pretty much as quickly as possible. And we started this only 2 years ago. A feasibility study done by a consulting firm did that initial modeling that showed us it could actually happen. We've been working with regulators and policy, trying to build some policy support around this. We've actually done these pilot treatment facilities now. We ran those where the water I brought today comes out of our pilots that have been running for about 6 months. We awarded a contract this morning for a $25 million, 1 million gallon a day demonstration facility in northern Suffolk. and we hope to obtain our UIC permits, which is underground injection control permits from EPA, sometime in mid-19, after we have about a year's worth of data from our demonstration project. So, I don't think we can move any faster than we're currently moving, and some of our staff would think we might be moving a little too fast at this point. So we have 2 test wells we've already put in, and the critical one for us was at our York River treatment plant. We are inside the edge of the crater, according to the maps. The crater's been described as an upside-down sombrero, and we thought we were out on the brim part of that. Turned out we were. We got through the crater material around 600 feet and found actually some really strong and good aquifer material below that. We need a little more work on the well to make sure we're connected to the whole aquifer, but if that comes true, we'll be able to put water in the ground there as well. The other well we have put in place is at the Nansemond plant, where our demonstration facility will be putting 1 million gallons a day in there in the very near future. So with that, I'm going to turn it over to Charles just to talk a little bit about the treatment technologies, and then we'll wrap it up with some cost.
Okay, so for the last 6 months or so, we've been doing some pilot testing of these advanced treatment approaches. And so these are the processes that would be added to the end of our existing wastewater treatment plants. And to put this in perspective, we're talking about not quite doubling the infrastructure that's already present. So this is a substantial upgrade. That red box that Ted showed that was advanced treatment is a big deal. This is adding a lot of additional treatment to our existing treatment plants already, and that makes sense if we're intending to go all the way to drinking water quality. We're testing 2 approaches, a membrane-based approach and a GAC or carbon-based approach. These 2 approaches have both been used in this application. I'll talk in a minute. There's a lot of reasons for us to be focused on the carbon-based approach and the processes associated with doing that. One in particular is producing a water that's most compatible with the geochemistry of the aquifer, and that's absolutely critical that we get that part right. From the objectives, what do we want to achieve with this? One is to compare the finished water quality between these 2 approaches. There is a bit more experience with the reverse osmosis approach. We've already shown, however, that the carbon-based approach is equally and perhaps maybe even more effective, more protective in a lot of ways. Gain some operational experience, establish some design criteria, monitor for compatibility with the aquifer, and really understand removal of emerging contaminants and other forward-looking parameters. So if we think about this, there's really 3 things that we're concerned about. We have to make water that is drinking water quality, and there are a lot of regulations that define how that needs to be done. That protects with respect to pathogens and chemicals and metals and so on. So from our standpoint of what we're concerned about, we need to make sure we're compliant with what is really would be characterized as drinking water quality. But in some ways, we need to go way beyond that because of the starting point in this case, and we understand that. So we need to be we need to ensure excellent protection with respect to pathogens and excellent protection with respect to organic chemicals, particularly focused on the pharmaceuticals, the hormones, the emerging contaminants that everybody is quite concerned about in this case, and that's a strong reason for doing this pilot. So this is what the pilot facility looks like. That's the membrane-based pilot, ultrafiltration in the back and reverse osmosis in the front. To put this in perspective, this is about 1/2000th scale of what it would be when we build out. Ted mentioned the demonstration facility. That's about 1/20th scale. So we go 1/2000, 120 full would be the intent here. This is a picture of the carbon-based facility, and those individual skids sort of contain the equipment that is required to do that, and I'm going to go through this schematic in every detail here now. No, I won't do that. So there's a lot going on. That this is a complicated little system to put together and to run. But what is equally complicated, and if not much more complicated, is the sampling and analysis that goes along with this. So from an investment standpoint, the sampling and analysis is probably twice the investment of the pilot. So we have analyzed for hundreds of compounds, lots of different viruses, bacteria, and protozoan pathogens, and so far, very good. So what are we interested in here? We're interested in the human health issues, drinking water, maximum contaminant levels. We don't have an injection standard in Virginia yet. But we're also interested in aquifer-centric issues. So we have an anti-degradation criterion that we need to think about, and we have to make sure that the water is compatible with the chemistry of the aquifer, and that's focused on things like pH and alkalinity and hardness. So preliminary results, both trains are meeting drinking water quality standards. In fact, we're well below that. We don't have any trouble complying with those requirements. That's not even, we're not even sort of close in that regard. All primary MCLs are being met. Our one challenge has been bromate. Bromate is formed as a result of ozonation. So if we add ozone, both for disinfection and for oxidation of organics and to make organic compounds more biodegradable, ozone reacts with bromide to form bromate. We've got that under control now. We knew that going into the pilot that was going to be a challenge. It took us some time and a bit of sweat to figure that out. We've got that solved, and we're way below the MCL for bromate as well. All secondary MCLs, which are focused primarily on aesthetics, are being met with one exception. And again, we knew this going in. The carbon-based system doesn't remove salt, and that's a benefit from an aquifer compatibility standpoint. That's what we want. Unfortunately, reverse osmosis removes all the minerals, and in order to get back to a point where it's compatible with the aquifer, we have to add all that back, and that doesn't make a lot of sense. So we need to be protective. We don't need to remove all the valuable minerals. The TDS is slightly high compared to the 500 milligram per liter, again, aesthetic standard. And this is for York River plant. We, of course, need to test this for the other plants. But sulfate and chloride are consistently low. So I only got to present one data slide. So Ted, I only got one. So this is what I chose. And it's a bit busy, but it's intended to be so. So this is what everybody's worried about. These are the chemicals of emerging concern, and we have more, but this list, this group is known as the Urethane 96, and so this is 96 compounds of emerging concern, all being analyzed at nanogram per liter levels or part per trillion levels. So this is sort of the best we can do as far as measuring these compounds at very low concentrations. And of the 96 that we analyzed for, conversationally, 20 to 25 or so were being detected in the current wastewater plant effluent. So if we went back all the way to the head of the wastewater plant, we would see a lot more red show up. Turns out that our existing wastewater plants are really protective against these compounds already. We get good removal already, but not everything. And so we have 20 to 25 left that were detected at least once in one sample. And if we look at the data here, of course, we have a lot less reds, and the columns to focus on here are the GAC effluent 1 and GAC 2 effluent and the UVAOP effluent. That's really effectively the finished water from an emerging contaminant standpoint. You see a few red squares. Those red squares are right at the detection limit. So we're talking very low nanogram per liter levels. And some of the compounds that are, as an example, that are showing up there are artificial sweeteners that start out quite high, it turns out. They're designed not to be biodegradable, and if they were biodegradable, they would cause us to the calories that we don't want, perhaps. And so they're a good marker in this case, and removal of those artificial sweeteners is actually a topic that a lot of people are interested in because they're a marker of these emerging contaminants, and they're at pretty high levels to start with. But we're doing quite a good job, and the data as a whole suggests that we're quite protective with a carbon-based advanced treatment approach. Aquifer compatibility, we're working on, but it's quite clear that a carbon-based approach or even a nanofiltration approach is generally a lot more compatible, whereas the reverse osmosis approach requires adding salt, hardness, and alkalinity. It's not common to add salt, but at the locations we would be injecting into the aquifer, we already have pretty elevated TDS, 1,500 to 2,500 or so, and so injecting water at 50, that's just a no-go. So if we want to be compatible, we need to leave some TDS behind. So the big questions remaining from the work here are evaluation of other plant effluents. The pilot testing has been done at one facility at this point. The demonstration facility will allow the same work to be done at a second facility, and then we'll consider the other plants. GAC regeneration interval, if we consider the carbon-based approach, GAC regeneration is a big factor with respect to operating costs, and that's of course an important question for us to answer. I mentioned before that bromate is an issue. We sort of, because we're taking the opportunity to drink the water and have tours for people to drink the water. Our approach with respect to bromate control at this point was to drop the biggest hammer we know of from a technology basis, but we haven't had the opportunity to sort of back off and see what's really possible. And so there's a lot of work to be done, and there's some other effects that has. Enhanced coagulation with ferric sulfate, which is probably going to happen at some of the other facilities. Disinfection byproduct formation is an issue because of the need to provide a little bit of chlorination of the water to protect the injection well. We need to verify that we won't be forming disinfection byproducts as a result of chlorination, very similar to a drinking water application in that regard. Performance during wastewater excursions, we just finished this testing, so the question is, what happens to the advanced treatment facility during a wet weather event when our wastewater plant, our existing wastewater plant, might not be performing as well as it does on a dry weather day? We had the ability to test that in this small pilot, and the conclusion is that it works great. No problem in that regard, and these advanced treatment processes are robust enough to handle that no problem. And the last thing we've done that we just finished was some virus challenge testing. So one of the opportunities we have with a small pilot facility is that we can afford to buy a very concentrated culture of viruses, a viral indicator, MS2 coliphage in this case, very concentrated culture of viruses, and simply feed it to the pilot and look at virus removal across these advanced treatment processes. There's no way we can do this in full scale, but we can add very high concentrations of viruses and look at that. And so we're showing, in this case, 9 logs, greater than 9 logs of virus removal across each of these two treatment approaches, advanced treatment approaches. A log is 99%. So 9 logs is 99.9999 times, right? Percent removal in to out. And we probably would show more, but we're below detection by the time we get to the end, even feeding 10 to the 9th of virus. So this is very encouraging for us to see that both of these systems are providing the level of protection they are. I'll just point out that by every method we've used to try to detect both viral indicators and viral pathogens, we haven't had any detection on any sample for the finished water that we're producing here. Now, Ted will talk about the costs.
Just another plug for the Eastern Shore school system. You know, you heard the brain surgeon or brain doctor up here earlier. Just heard Charles Bott. You know, we had a whole panel full of folks. I don't know what's going on over there, but they're brilliant people. So the cost summary. So when this was posed out to us, when our consultants finally made this presentation, we saw it had all these possibilities. I think my staff was a little sheepish of throwing the number out there, but it was $1 billion, and I was like, yeah, that's great, let's go. And like some of the earlier speakers saying, that's not something you want to bring to Richmond. It's something we don't really have to bring to Richmond. So HRSD is a large organization with a $4.4 billion capital plan over the next 20 years. 2.2 of that's this wet weather work that EPA is making us do. And I think we've actually looked at that. So we've got rate projections in our budget every year that show how we're going to support that $4.4 billion investment over the next 20 years. And by rearranging some things and slowing down the wet weather work, we can actually put this in front without changing that rate projection. So we can actually afford to do this. Our rates are still going up, but they go up either way. It's which projects we determine to do first. And we really believe with the environmental benefits of this project, this is the one to work on first. We'd still do some critical wet weather work during that first 10 years while we do the build out, but we would be doing this work predominantly with that money. So went over the benefits. I don't think I need to belabor that. They're big. Why now? Well, for us, there is some urgency here. I mentioned the consent decree. Our plan is due to EPA in October of 2017. If we submit that plan without this project and they approve it, we're legally bound to execute that plan and schedule, which pretty much closes the door on this opportunity for 20 to 25 years. We don't think that's acceptable, and so we're really working hard to make sure we can integrate this with whatever we propose to submit in October. The TMDL deadline, I think everyone's aware of 2025, is looming out there. We obviously want to have this in place and be able to do some of the trading and have some of the plans in place in Virginia's upcoming WIPs to show how we're going to make our TMDL goals. The groundwater scarcity is going to continue to go downhill. The unpermitted withdrawals are estimated to be increasing at about 1 MGD per year, and that's going to continue to go that way. And we don't know where groundwater policy will end up, but that's still a real concern over the next many years. And then our treatment plants themselves will get hit with some additional regulations in the next probably 10 to 15 years. Our timeline is we're finishing up this pilot work now. Those room scale pilots have been operating for about 6 months. We'll start construction on that demonstration pilot in our northern Suffolk plant in this January. I just signed that contract this morning. They'll be finished in 1 year. We'll get about a year's worth of data. We'll apply for our permits so we can start constructing in the 2020 timeframe. And really, mainly from a financial and operational standpoint, we've got a 10-year build-out. We're going to be doing major construction at 7 plants, $1 billion worth. We just can't do that much faster. So anyone that says any regulations or anything else are slowing us down, I don't see that. EPA has been wonderful to work with on the permitting side for this. DEQ, VDH, everybody's been at the table rolling up their sleeves and helping us figure out how to make this happen. We've got a lot of support from both the congressional delegation and the governor, and we've been making a lot of news these days, and it's been pretty positive. And the reaction to the citizenry, which we expected to have a lot of sort of the ick factor negative uprising, has not been there. So I attribute that to the timing is right. A lot of other water crises in the United States and across the country and the world have really set the stage to have people more accepting of this concept. And with that, I think we've got time for questions, right?
Sure, nobody has any questions.
Thank you. Excuse me. Even though I'm no longer with EPA, I love to hear you say that EPA has been wonderful to work with, so thank you.
I won't say that about all of them, but let me
Sorry about
clarify.
my earlier Mr. Whiskers comment. I meant that in the most loving of ways,
Yeah, I know,
Ted.
you,
So.
you and Mr. Whiskers go way back.
So my question is with nutrients. So conceptually, I love the idea of this. I'm not a groundwater hydrologist, so I can't speak to the impacts it would have on land subsidence or saltwater intrusion, those things. But I know math well enough to know that taking 5 million pounds of nutrients into the bay and going to zero is a pretty good thing. But over 20 years of working on this, what I've kept hearing is we're bumping up against the limit of technology as far as removing nitrogen and removing phosphorus. And I kept looking, Charles, for the numbers in there. I don't think they were in there. But as far as a discharge from a nutrient plant, 3 milligrams per liter is about limit. Even with the top-notch filtration, biological, phosphorus is a lot lower than that. So if you inject this in the ground, will you be able to take straight whatever's coming out of the end pipe and put it in the ground, or will you have to treat it to even lower levels of nitrogen and phosphorus? Because I've been told that you can't get any lower. So where does it go?
Okay, so there's a couple of interesting issues. So to start at the wastewater plant, the conversationally, we need to be less than a TN of 5 or so. As we go through these advanced treatment processes, the ammonia, at least on the carbon-based approach, the ammonia is gone, right? The ammonia is really below detection, almost consistently below detection. So there's no ammonia there. With respect to organic nitrogen, this string of processes, these advanced waste treatment processes, do a really good job, right? This is, when people talk about limit of technology with respect to our existing wastewater plants, they're not talking about adding what we're talking about adding on to the end, which is, how do I say, tricked out drinking water treatment, right? I mean, that's what it is at the end. Nobody's talking about that when we talk about limit of technology. This is significant. Like I said, it's nearly doubling the infrastructure that we already have at a treatment plant. The second thing I'll point out that from a nitrogen standpoint, to be protected from a drinking water standpoint, nitrate has an MCL of 10, nitrite has an MCL of 1. So we need to, of course, be very protective of those two values, but that's a lot more than we're talking about from a Chesapeake Bay standpoint. So our discussion has been that we probably need to have a nitrate concentration less than 5, less than 3. So we can, with the bit of nitrate removal and nitrite removal, a complete nitrite removal across this advanced treatment system, we need to be protective with respect to nitrate going into the advanced treatment facility, so that we can ensure we need to ensure all the time that nitrate is well less than that MCL. So yes, there is some nitrogen remaining in the finished water that gets injected into the aquifer, but there's nitrate present in drinking water too. Yeah. Does that answer your question?
Yeah, I can go on forever, Bill.
Well, just to follow up with that, I guess two questions. One is the follow-up to that. Why don't you just take the water from the advanced drinking water treatment and just release it the way you release wastewater, treated wastewater now? And then the second question to that is, what are the benefits? I mean, there are benefits, or you see benefits of injecting it, but I'm concerned about the slow rate of diffusion of water through the aquifer. How many injection wells are you talking about? Are you going to be able, to move the water through the aquifer in a reasonable fashion?
Sure. So we'll start with the first part of your question, which was why don't we just treat it to this level and discharge it to surface waters? I would argue that that's a waste of societal resources. So the waters we discharge are very protected by the current permits they receive, and their designated use is aquatic life, vegetation, or recreation, contact recreation. Those are the intended uses of the York, James, Elizabeth, Rappahannock rivers that we discharge into. I don't know anyone, I'm not sure anyone in the room would go out in any of those bodies of water and take this glass, dip it in, and drink it. It's not a designed drinking water source. The Potomac Aquifer is a drinking water source. So we're adding this treatment to be protective of where we're discharging the water. It would be a waste to add this if we didn't need to for protection of the water we're putting it into. So that's the answer on that piece.
Where are the cost savings?
So there are no cost savings directly to HRSD, and so the cost savings are regionally, as far as potentially the offset on the stormwater piece, the regulatory stability that we think, and we haven't tried to really calculate what this looks like, but essentially every time we have to go do a major plant upgrade, it's very disruptive and very costly to work around the existing. So doing it all at one time instead of 6 times over the next 30 years has some savings to it. Then we've got, if we're successful at slowing down the rate of land subsidence by 25%, protecting those wetlands that would be inundated and maybe even low-lying areas in Norfolk and other parts that suddenly get 50 years of additional useful life. No one's put a number on that, but it's huge. And then finally, economic development of Eastern Virginia. You heard Delegate Hodges talking about the low wages and the lack of opportunity there. It's essentially going to become isolated, and there will be no further development on Eastern Virginia if we don't have a water source. And so putting this water into the aquifer really creates a future for Eastern Virginia that doesn't exist. And if we don't do this, even if we cut everyone out, you're not going to be able to develop great stretches of that part of the country, or Virginia, without a water source. And there's not surface water available. It's, it'd have to be desalinated, very expensive. So, and then to your question about the water moving, our water doesn't need to move very far. We just need to repressurize the aquifer. And that's what the modeling is showing, so that as our water goes in, it's just essentially pushing water molecules next to it out. And so it's getting this giant repressurization of the whole aquifer. And so anyone could tap that aquifer in the future, and we don't know what the ultimate safe yield would be. But according to this, we could withdraw the full permitted amount almost in perpetuity after 50 years of us putting water in the ground. And there'll be some immediate response, within the first few years, but it's definitely got some. So coordinated with DEQ with the appropriate permit cuts to get the right-sized permits with a new source should open up opportunity in Eastern Virginia that there's no other way to get to. Oh, the number of wells? It's each well is about 3 to 4 MGD, a million gallons a day. And so there'll be a series at each of our treatment plants. The treatment plants we're working at are anywhere from 10 to 30 million gallons a day plants. So they'll have a header and a series of wells at each plant.
And as you increase the pressure locally near those injection wells, does that make it more difficult to inject?
The modeling showing about 10 PSI to start. It's a thirsty aquifer. We're a couple hundred feet above it. It's not going to take much to put water in it. And at the end of the 50 years, it's around 40 PSI. It's still not very high, and that'll be dependent on, if there's more users pulling water out, it starts reaching some sort of equilibrium at some point.
You showed a chart about the swift discharge. Would you expand on that? Is it highly concentrated, and where is it discharged, or what's it composed of?
I think that was, that's really just not what we're discharging. It's just total volume that we've discharged under, if I get back to that slide. That's still the same. Sorry about that. Way up in the front of it. There we go. So that swift discharge is just still our, that, in that case, that's the TP and TN, that's the same. But I think this was the chart you're looking at. That is just our treated wastewater meeting our current standards during a rainy day. So the facility will be sized to handle flow that we see on a 95% of the time. There'll be a certain period of time that we'll have to discharge when it's beyond the capacity of those wet weather facilities.
I had a question. You showed the, I guess, the monitoring work that was done on the Franklin paper mill and, the changes when the paper mill, I guess, ceased operation for a period of time. I wondered, has there been anything done similarly with the West Point paper mill? Because my understanding is, and please correct me if I'm wrong, their use is about 10 million gallons a day of water. I don't know, maybe that's...
I think West Point's closer to 20, Scott.
Oh, well, more than what I
19.
thought. So I guess where I'm going with it, since that obviously is a significant user of water, have they been looking at, and I don't know if you know this, more reuse technologies, and is the Commonwealth perhaps looking at, I don't know, incentives perhaps to have them, reconsider the amount of, if you will, of their water budget?
I'm probably not the best to address that. I do know that they're working with DEQ on trying to find ways to reduce the amount that they withdraw on a regular basis. And I don't think any of us are ready to say what that is at this point, but they are trying to find ways to do it. A lot of times we get questioned, and I'll just throw this in there, why don't we just pipe our discharge, our highly treated water, right to West Point so they don't have to pull any water out anymore, right? Sounds like an easy solution. Well, it's fraught with some issues on our end. One, we've already been in that business. At our York River treatment plant, the refinery right there used to be owned by Giant. They entered a deal with us to take 500,000 gallons a day of our water. We added some infrastructure to treat it not as highly as this drinking water, but to meet their industrial needs. We did that very successfully, and up till about a month before we stopped doing it, they were talking about expanding to 750,000 gallons a day, and then they closed. And so the local folks didn't even know that they were closing. They were sold and became a fuel depot as opposed to a refinery, and total change of operation for economic reasons outside of our control. Big concern is we build a pipeline to West Point and at a cost of maybe $200 million to try to deal with their water issue, and they shut down for other economic reasons at some point in the future. And so that's a big pipeline to nowhere, and then we're stuck with what do we do with the water at that point. And you lose all the added benefits of, I refer to this as the wireless solution to water challenges in Eastern Virginia, because you don't have to be at the end of the pipe. You can be anywhere in the aquifer and pull the water out essentially. So it's a much broader solution as opposed to just having a pipe go to one location.
My name's Brent Foltz, thank you. Can you cover quickly with me what social or financial assurances you're going to give to the Commonwealth in case of a catastrophic failure? I've heard you say this is all working, but you're asking the whole room to believe you. So if you all put up a financial bond
You're finding it a hard time.
compensate when it is a complete failure of the hydrologic system?
Sure. So, we got a couple big built-in benefits. We continue to operate and maintain outfalls and permits for each of the treatment plants. We'll have a series of critical control points like any other water plant in the processes. And anytime we hit certain limits and see that the process isn't working, we just start discharging again out of our outfall. We shut it down and fix that. So that's the operational controls, easy to do. We're not abandoning our ability to discharge at that point. Got some other complications if we had to do that long term, but that's it. The other piece is a lot of folks say, well, what happens if something goes wrong in the ground, in the aquifer? You're pumping away your tracer well, you have a series of wells around, you're monitoring all the time to see when your water shows up, what's in it, have you done anything to the aquifer? the experience we've learned from Chesapeake and modeling is because the water doesn't move very far, you just quit pumping at that point. And worst case is we'd have to pull water back out like Chesapeake does today. It doesn't move very far from the well. So you're really not causing any issues broadly beyond a very small area around your wherever you're injecting the water. So I think there's pretty limited, especially since it's been done widely in the United States and other places successfully, the risks are fairly low at that point.
So will you or will you not be funding a catastrophic event in case other regions depend on you and you reach the situation you just described?
The great policy question, couldn't tell you. Hasn't been brought up as a requirement. And we maintain pretty significant cash reserves now. We'd probably have some environmental insurance or something around that. Yeah, we don't need to be doing this. I mean, this is really, I want people to understand this isn't HRSD looking for an easy way out. This is HRSD looking for a creative solution to a variety of problems that the Commonwealth is facing. The easy way out for us is to continue to do what we do. We do it very, very well. We exceed permit limits every day. I mean, we're a top-ranked wastewater treatment organization. And I know I get in front of audiences sometimes maybe a little defensive, but I get the feeling people think we've got something in this for us. There's nothing in it for us. I mean, what's in it for us is for our children and for the Commonwealth. And maybe that sounds corny, but we are here trying to do something. We spend our lives trying to improve the environment, and we really aren't doing. We still pollute. I mean, we put out water that's highly treated, meets the needs of the receiving bodies, but we don't feel that great at the end of the day. We're going to feel wonderful if we can pull this off.
I had an opportunity to take a look at the latest set of minutes from the Eastern Virginia Groundwater Committee, the joint committee between work groups 1 and 2A. And there were some discussions in there that I thought made some sense. First off, I want to applaud what you're doing. But what I think I'm concerned about is anytime you deal with complex systems, the types of variables that are involved in this are sometimes beyond what we know. And what was pointed out in those set of notes was that a lot of your modeling that you're using off of the DEQ model that you're talking about is only within a 50-year time frame, when in fact what you're putting into place is something that will go on for hundreds of years. Now, I'm not advocating that you stop what you're doing, but there are limitations into that. And so one of the things that was pointed out in there is the need to have some ongoing set of research involved in that. And I don't think that that necessarily revolves on you, but on the Commonwealth and the DEQ to put those sorts of parameters in there to monitor the complexity of the system as it evolves. And once again, I don't think it all falls on you, but it is a responsibility of the Commonwealth to participate and for you not to put a financial guarantee to the system. Could you address those sorts of limitations that you may see?
Sure, and obviously modeling is the only thing we've got, and I'll say all models are wrong and some are useful, and we're hoping that we're using one that at least is comparing the prediction of disaster versus the prediction of recovery. So we're using the same model, we aren't in dueling model land. But going to your point, I firmly agree with what you're saying about policy around long-term monitoring and trying to figure out what that looks like, and we're very open to participating in those discussions. I think the model for Virginia is the Upper Occoquan system, where they created the Occoquan Monitoring Lab, part of Virginia Tech. It's long-term, it's up there, they're constantly monitoring what's going on. We probably need a similar model. It might not be the same model, but something similar to monitor us going forward, because whoever said it, I'm not always going to be here, and I wouldn't believe me either that says that HRSD is always going to do the right thing for the next 100 years. So we do need something to assure the Commonwealth that this continues to be done correctly, monitored, and look at the long-term implications. But I would agree with that. I think we've got a model right here in the state that's been very successful since the 70s, and that'd be a great place to start.
Are there any additional questions?
Our demonstration facility that we're getting ready to build, we actually are building research space and office space in there in anticipation that maybe that model ends up happening and they need a house. So we're very much in favor. And I think your next panelist will have hopefully Mike can address some of Orange County. Mike and Jeff can talk about the Orange County experience. We're also having a independent third-party expert panel reviewing what we're doing at arm's length from us as well during this process. So we're trying to build all that in, but I do think the Commonwealth has a long-term commitment to this as well.
Thank you all. It was a terrific panel. Thank you. Thank you.